Hello to everybody. This is the fifth week of algorithmic design, and I hope you are well. As you see, I for sure need an haircut, but unfortunately, again, it's not possible to have it. So sorry for my head. Yesterday, I was contacted by your representative, and she told me that you are in trouble with the homework. So first of all, I want to ensure you it's not really a problem. We will find out a way to solve this problem, this issue. And I asked her to collect all your issues. So basically, I would like to know which homework is the worst one. I mean is the most time demanding one, and so we will try to figure out a way to solve this problem. Okay, don't worry about the homework. I decided to avoid to ask you the solution each week, just to let you organize yourself as you prefer. Anyhow, from one end, I'm really sorry for this problem, but from the other hand, I'm in some sense happy. I'm sorry for you, but I'm happy because from the very first lesson I told you that I want some kind of interaction, and I said that I want to understand what's going on with your study and with the homework. So knowing that you are in trouble, I mean, from a certain point of view, is a good thing because I know what's going on. Anyhow, as I said, until now, don't worry. We will figure out a way to solve this issue. The last time we conclude our trip on the sorting problem, we saw the selection algorithm, which actually is not really a sorting algorithm, but is basically used to figure out the position of the ith element in an array if the array was sorted, and we saw that we can use it to improve the asymptotic complexity of quicksort in an easy way, because we can use it simply to pick up the best pivot for the partition procedure. So today we will move into a different topic, which is dynamic indexes. Okay. So first of all, I want to introduce the topic by providing some motivations. As usual, I really think that an important part of your study is to understand why something is useful. We saw that, for instance, the sorting problem is useful because it give us the chance of using dichotomic search in searching some keys inside an array, and so we understood why sorting is so important. Now, why dynamic indexes is so important? Let us consider a very simple example, which is an example in which we are dealing with a registry office. So the registry office is the office where newborns are registered, and of course for each newborn we want to record some kind of data. So for instance, the name of the parents, the birthday, and so on and so forth. Okay. So hopefully this registry will be updated quite often. Okay, so every day there will be more newborns, and so the database, let's say, change quite often. Now, what's the best strategy to query this data set according to birthday? Okay, so we want to find, for instance, all the newborn, all the person born in a given date. So how can we achieve this goal? How can we find all the person whose birthday is, I don't know, the 9th of April 1974, for instance? Okay. Well, we have three, let's say, first possible strategies. The first one is, of course, the naive, which is to scan all the data set. And we understood that performing this strategy, going through this strategy, may cost us up to, this should be a big O, of course, up to the number of objects in a data set. Okay, so scanning all the data set to searching for all the person living a given day, whose birthday is a given day, takes a time which is theta of n if we does not collect all the person in birth in a given day. Okay, so once we have discovered the first one, we are not sure that this is the only one, so we need to keep on, and that's why this is theta of n. What if we sort the dataset by birthday at each insertion? So let's figure out a situation in which our dataset is stored in an array, and every time we insert a new element, we need to perform a sorting, and that sorting allows us to, of course, query the database by using dichotomic search. Well, the time required to sort of the whole array, of course, is theta of n per insertion, and this is because we can apply radix sort on the birthday and the birthday date, and then by applying dichotomic search, this takes theta of log n. Going back to the previous example, I was saying that it depends, okay, I'm talking about the complexity of the first strategy. It depends on how you deal with many people, burning in the same day. So if you basically have a list, an array in which each element of the array is a list of people whose birthday is the same day, okay, then once you have found that element, you can avoid to skip the whole array. And this is a way to decrease this complexity from theta of n to big O of n. Okay. If otherwise you decide to maintain the array all the persons, okay, and as I said, you discover one of this person born in the day you have queried the data set. Basically, you are not assured that this is the only one, so you need to keep going until the end of the array of the data set. And in that case, the complexity is big O of n. Okay, so the complexity, the lower bound complexity for this strategy really depends on the data structure you use to store the array, to store the database. So if you store for each cell of the database, you store a person, the complexity is theta of n. If for each cell of the database you store a list of people whose birthday is the same, so all the people having the same birthday are contained in that cell, then you end up with a big O of n. Okay, of course you have a drawback in that case, in the second case, in the latter case, because you are forced to, when you want to insert something inside the database, you are forced to scan the whole database, at most scan the whole database to find out the cell in which that day occurs. Okay, and so going back to the second possible strategy, a possible strategy is to sort the dataset by birthday at each insertion, which, as I said, takes time theta of n per insertion, because we may apply radix sort to sort the whole dataset, plus theta of n per query. And this is okay. I mean, it's not really okay, because again, for each insertion takes this time, for each query takes this time. But what if we want to perform a search by name, for instance? We have to resort everything at each query. Okay, and this is not really nice, let's say. So what about another possible strategy? Could be to sort the whole dataset by birthday at each query. Let me go back again to the previous point. It's not clear. More people are born on the same day, theta of n, and only one people registered the same day. No. I was saying that. So let me repeat the point here for this strategy. So the complexity, this complexity depends on the data structure you choose to store the whole data set. So if you use an array in which each element of the array represents one person, and of course you may have many persons whose birthday is the same, okay, in that case, once you have found one cell in which a person is born as a birthday, the day we are querying the dataset, you are not guaranteed that there are no more persons having the same birthday. And so you are forced to scan the whole dataset, even though you already found one person on the date you are querying the dataset. And that's why here I am reporting theta of n. But what if instead for each cell of the dataset contain a list of people instead of a single person? So the list of people whose birthday is the same. So let's say I don't know, the second cell of my array contains all the people whose birthday is 31 of December 2009. Okay. In that case, once I found the cell containing the specific date I'm querying the dataset, I can conclude my query. Okay, and that's why in that case the complexity would be big O of n. So it depends on the dataset. Well, not on the dataset, but on the data structure you are using to represent the dataset. In any case, the worst case scenario, so the upper bound for this strategy is big O of n. Okay, and what about the third strategy? Well, the first strategy for each query we are sorting the data set, and this of course takes time theta of n, because again we are using radix sort to sort the data set, plus theta of n, big O of n big O of n for the query, and then we end up with a theta of n. Okay. So in all the cases, we are spending a time which is, in the worst case, big O of n, which is, of course, much more than applying dichotomic search on a sorted array, and if you think that this may occur in a dataset containing billions of people, of course is not acceptable. Okay, how can we deal with this scenario? Well, the point is that the dataset often change, then array is not more suitable for data structure, and we need a new data structure to achieve this goal. Okay, and the data structure we are searching for is a data structure in which we want to be able to add new data in an easy way. So by easy I mean with a low complexities, worst case scenario complexity. We want to search data, and of course again we want a low complexity for searching data, and we want to remove data because eventually every one of us will die, and so we want to update our records. Okay, and this is what we want to do. That's all. The idea is to build something called index. So what's an index? An index is an auxiliary data structure which is meant to perform efficiently all these three operations. Okay. Now, you probably, for sure, you are an expert of binary search trees because you saw them during the first part of this course. However, let me go through them from the very scratch, okay? So we can understand what's going on, and we can figure out the complexity of binary search tree. So binary search tree is basically a data structure meant to provide an index. And they are basically trees, and we already introduced trees at the very beginning. They are basically connected cyclic graphs, and we saw that we need to provide a root for the trees, at least from the computer science point of view. And let me use the following notation for them. We will have the left and right children of x, and we will denote them by writing x dot left. This is the left child of x, and x right dot right, meaning the right child of x. Okay. And of course we need a way to deal with the parent of x, which is this one, and of course we need to evaluate the value stored in a specific node, and this is the key. So by writing c dot key, I know the value in x. And what if my node hasn't any left child? Then to do it, to test this condition, so to test the condition in which x hasn't any left child, we may apply this piece of code. So to test it, we simply verify whether x.left is equal to nil, and if this condition holds, then this means that x means the left child. Okay. And what about the root? To test whether or not there is a root, we simply need to test whether its parent is nil. Okay. So on all the nodes inside a specific tree, the only node whose parent is nil would be the root. And that's all. So by using this notation, we are now able to provide some very useful functions, and this function takes time constant. Takes constant time, for instance, to test whether a node is the root. As already said, we simply need to test whether its parent is nil. If this is conditional, then the node x is the root of the tree. Now, how can we test whether x is the right child of its parent? Well, this is quite easy to do. Well, first of all, we need to test whether x is the root. If it is the root, then of course it couldn't be the right child of any node. If it is not the root, then we simply have to go through the parent link, which is dot parent, and then test whether x is equal to the right child of its parent. And if this is the case, we can say yes, x is the right child. Okay. And again, this takes a constant time as testing whether x is the root. Of course, we can also test. We can also get the siblings of x, so the other child of x parent, and this is done by first of all testing whether x is the right child. This should be left, of course. This is wrong. So if x is the right child, we simply have to get the parent of x and then the left child, otherwise the right child. Okay, so this should be left and this should be right. And of course we can get a function we can write a function to get the side of x, which is childhood side, which tells you whether x is the right child or the left child of its parent. We can get a function to reverse the side. So if I'm providing this function with the left, I get a right. If I'm providing this function with a right, I get a left. Okay, quite easy. Another function we can get is, of course, a function which gets the child of a given node according to the side we are searching for. So if we are searching for the left side of the if we are searching for the left child of x, we simply call get child with x and left, and we end up with the left child, otherwise with the right child. Okay, we will see why this function is useful. Of course, is a way to generalize this notation. This notation is specific, so once I write this notation, I already know whether I'm interested in the left child or the right child. While by using this notation, I can encode a get child without knowing the side, of course. And we may also be interested in a function to set a child. So once I have the node x and the node y and a side for the new child, I may want to place y in the set y as the child of x on the side. Okay. So for instance, let's assume I want to set y as left child of x. I simply need to call set child x left and y. So if side is left, of course I assign y to x left, otherwise I assign x right, y to x right. And then once I have updated the right or left child of x, I need also to update the parent of y, and this is done exclusively when nil is y is different from nil. So if y is nil, of course this cannot be done, and of course is unnecessary. Otherwise I need to to update the parent of y and setting it to x. Okay. Again, here we are not performing any while loop, so this function again takes time, while for loop. So again, this function is theta of 1, takes time, theta of 1. What about this this function? Well, of course, we may be interested in the uncle of a given node. We may be interested in the grandparent of a given node, and so on and so forward. All these functions, we may be interested in building a new node, providing the value we want to store as a key. So this is quite easy. We are assigning v to the key, and all the links are set to nil. So again, this is quite easy functions, and they are, all of them are theta of 1. Now, what's a binary search tree? You already know it, but let me go through it. As for the heap, we need to provide a total order, and so once we have provided a total order, we may say that all the keys belonging to the binary search tree satisfy what is called BST property. So all the nodes that belongs to the right for all x, all the nodes belonging to the right subtrees of x contains a key which is smaller or equal with respect to the total order to the key of x, and all the nodes belonging to the right subtrees of x are contains nodes which whose keys is greater or equal with respect to the total order to the key of x. Okay, so this is the BST property, and this property holds not only for the root of the BST but for all the nodes in the BST. This is quite important. Okay, so just to have an example, this is a BST. All the nodes you can see as a key the value inside the node itself, and here we have also the representation for the nil, just to say that for each node we have both the left child and the right child. They may be simply a nil value. Okay, so if a node does not have, is a leaf, so does not have any children, it actually has two pointer to nils, and this is the representation. However, for simplicity, we will assume we will draw all the binary search tree in these ways. So we will remove all the nodes. So in drawing the binary search tree, I will remove all the nil leaf, let's say, simply to avoid to draw so much. They are actually these nodes, these leaves are not really needed, but they are useful to generalize, and we will see in a while why. All the discussion. So it may be useful to consider them actually. Okay. Great. So once we have a binary search tree, we can easily implement an in-order visit. So what's a visit? A visit for a tree is simply a procedure which go through all the nodes and in a specific order. So an in-order visit basically print all the nodes, visit all the nodes belonging to the right child of each node. Left belongs to the, an order visit all the nodes belonging to the left subtree of each node first, then the node itself, and then all the nodes belonging to the right subtrees of the nodes we are dealing with. So in this case, for instance, an in-order visit goes through before visit 4, go through all the nodes in these subtrees. Before visit this node, go through all the nodes in these subtrees, and since these subtrees basically contains only 0, only the node whose key is 0, visit 0, then visit 1, then these go through all these nodes, and these nodes contain exclusively 2, and so on and so forth. Okay, so this is an in-ordered visit, and this can be easily done in a recursive way. So an in-ordered visit can be done in this way, recursively, of course. We can start from the root if the node we are dealing with, and here you can see why it is important to consider the leaves, the nil leaves, as nodes, because we are able, by using the nil nodes, we are able to provide a recursive algorithm for in-order walk, an easy recursive algorithm for in-order walk. So if the node we are dealing with is not nil, we go through the left subtrees, then we print the key of the node we are dealing with, and then we go through the right subtrees. Okay, and this is an in-order walk, so an in-ordered visit. Now, what about searching for the minimum and the maximum in the binary search tree? Well, due to the binary search property, so the one which tells us that dealing with a node to search for, if we are searching for the minimum, we simply have to look at the right node, the node on the left. If we are searching for the maximum, we simply have to look at the nodes on the right. So the minimum in this BS tree is, of course, the first node on the leftmost branch that has no left child. So the minimum here is among this branch, and so the leftmost branch, and I need to find the last node in the leftmost branch which hasn't any left child, and this is it. Okay, so this is the minimum among all the, so this node contains the minimum key among all the keys on the tree. And what about the maximum? Well, the maximum, again, by using, so this is the minimum. What about the maximum? Well, again, due to the BST property, if we are searching for the maximum, we need to go to the right, and so the maximum will be the first node on the rightmost branch, which hasn't the right child. So this node has a right child, this node has a right child, this node has a right child, so hasn't any right child, so this should be the maximum, and this is the maximum actually. Okay, so going to the code, it's quite easy to find the minimum and the maximum of the BST, and we can provide two quite general procedure to find the minimum in a generic subtree of the tree, and this is it, and the maximum in a generic subtree in the tree, and this is it. Okay, and okay, this it's really nice to see that you don't even need to compare anything to find the minimum and the maximum on BST. You simply have to browse it, and searching for the first node on the leftmost branch hasn't a left child, and the first node on the rightmost branch which hasn't a right child. That's all. Now, what's the complexity of these two procedures? Quite easy, is big O of 8 of the tree. Okay, since we are searching, so this 8 of the tree is of course the 8 of the BST. The 8 of the BST is the length of the longest branch in the BST. Okay, so since here we are browsing a branch of the BST, the worst case scenario is that you are searching for, you are going through the longest branch, and that's why this is a big O of A of T. But the point is, we don't know the true weight of the tree at the moment. Okay, so is there a way to know this 8? At the moment we don't know. We will see. Now, what's about searching for the successor of a given node? So let's say, let's assume we want to find the successor of a number of the node whose case is 5. So by successor I mean I want to find, given a node, I want to find a node whose key is the next one with respect to this total order with respect to the key of the node I'm dealing with. So here, for instance, I'm dealing with this node. I want to find the next value, the value next to 5, just next to 5. Okay, in this case the value next to 5 will be this one, the 6. So how can I find it? Well, of course, a naive algorithm would be the one of going through all the nodes on the BST, but we can do much better than this, of course, and it's quite easy. So finding the next node is just finding the maximum among the maximum among the values stored in the right subtree of 5. Okay, so since we are searching for the next one with respect to 5, next value with respect to 5, we need to find something in the right, due to the BST property, we need to find something in the right subtrees of 5. Okay, and since all the values in the right subtree of 5 should be greater or equal than 5, then we are searching for the minimum among that value. So a possible way to discover the successor of this value is to search the minimum among the value on the right subtrees of 5. This is a possible value, but what about a situation, so in this case of course is 6, but what about a different situation in which we don't have any right subtrees? So for instance in this case, so what's the successor of 2, since 2 hasn't any subtrees? Well, in this specific case, we need to find the nearest right ancestor. So again, due to the BST property, well, first of all, let me say what's a right ancestor. The right ancestor is a node whose previous ancestor of 2 is the left, on the left side. So for instance, the right ancestor, the nearest right ancestor of 2 is this one, 4. Why? Because to reach 2 from 4, we need to move on the right and then go through the leftmost, well, to go on the left and then move on the rightmost branch from 1. Okay, so the idea is to go from one node up to the root, moving on the right until a point in which we can move moving on the left until a point in which we can move on the right, and this will be the nearest right ancestor, and this will also be the successor of the value we are dealing with. Okay, so in this case, for instance, I go to 1, and then since the parent of 1 is 4, which is on the right with respect to 1, 4 is the nearest right ancestor, and 4 will be the successor of 2. And this is due to the BST property, of course. Okay, so this is the pseudocode. It's quite easy. So if x has a right child, so if x right is different from nil, this means that x has a right child, so we can find the successor of x simply by looking at the minimum in the subtree rooted in the right child of x. Quite easy. If this is not the case, then we need to go, we need to have a look at the parent of x and test whether x is the right child. Well, of course, this can be done until the parent of x is different from nil. So this condition holds exclusively when x is the root, of course. Okay, so while this condition holds and we are dealing with a node which is the right child of its parent, we keep going through, so we keep going towards the root. So we keep moving towards the root until a point in which either the parent of the node we are dealing with is equal to nil, meaning that x is the root, or we are dealing with a node which is the right child, the left child of its parent. Well, in both the cases, we need to return y. So if the node we are dealing with is the left child of his parent, well, his parent is the nearest right ancestor of the node which was passed as parameter of successor. So we may return it. Otherwise, if this is not the case, we end up in dealing with the root, meaning that there are no successor for the original node, and so we need to return nil. Okay, and that's it. So what's the complexity of this procedure, of this pseudocode? Well, finding the minimum in a subtree, we saw it before and takes time, big O of 8 of the BST, and this procedure basically may go through a whole branch going from a leaf up to the root. So consider, for instance, the case in which we are querying the successor of the the rightmost branch of the tree, and the successor of the leaf on the rightmost branch of the tree. Well, this of course end up with the root. So we went through all the nodes from the rightmost leaf up to the root, and that's why this part may cost time big O of 8 of the tree. Okay, so again, finding the successor of this of a node may take time. Takes a time which is linear with respect to the 8 of the tree. Okay, just what about searching a value? You already know it. Searching a value on a subtree is on a BST quite easy. You simply have to apply the BST property. So from the root, you have to test, let's assume we are searching 3, you have to test whether the key we are searching for is greater or equal to the key of the node we are dealing with. If it is equal, of course, we discover the node and that's all. Otherwise, we have to test whether the query key is greater or equal to the node we are dealing with. If it is this the case, so if the query is greater or equal to the node we are dealing with, we have to move on the right side of the tree and keep repeating on the right subtrees of 4. Otherwise, we keep moving on the left subtrees of 4. So 3 is smaller than 4, so we need to test to search for it on the left subtrees of 4, and so we move on the left child of 4, which is 1. 1 is greater than 3, so we move on 2, and 2 is smaller than 3, so we again need to move on the right side, which unfortunately is nil. Okay, again here you can see why is in some sense important to deal with nil nodes. So they are not really useful from a functional point of view, but they are useful in dealing with all these cases. So dealing with the cases in which we want to search a given value inside a BST which doesn't contain that value is much easier if you think to have nil nodes. Okay. So searching for free we end up by searching for free we end up with a nil node, meaning that the number 3 is not contained in BST. Quite easy. So this is the code, nothing more, we already saw it. So so we are searching for the value v in the subtree rooted on x. Of course, at the beginning of computation, x will be the root of the tree, but it may change from time to time. So we generalize it by searching on the subtree. So searching a value in a subtree is simply performing this while loop until x is different from nil. So until x is different from nil, we keep querying, asking ourselves whether the value we're searching for is greater or equal with respect to the order we are dealing with to the node key. If this is the value, of course, we may also test the opposite relation, so testing whether v is smaller or equal with respect to the key. If this is the case, well, the key of x and the value and the value passed to the function are the same, so we may return the node containing that value. Well, we have to return the value, the node containing that value. Otherwise, if this is not the case, well, since the value is greater than the key we are of the node we are dealing with, we need to go through the right subtrees of the node, and so we need to deal with the right child of the node passed to the function. This is due, of course, to the BST property. If this is not the case, so if if v is not greater or equal than the key of x, then it should be smaller or equal because we are dealing with a total order. This means that we need to deal with the left subtree. And so we move from x to the left child. Now, what's the complexity of this procedure? Again, at each iteration of this while loop, we are moving from a node to one of its children. Meaning that in the worst case scenario, we are dealing with a number operation which is big O of 8 of the 3. Okay? Quite easy. Now let's see how to insert. So we understood that searching for a value is rather easy. Well, what about inserting a value? Well, inserting a value, again, is not that difficult. The first step is to search for that value inside the BST. So searching for that value inside the BST may end up in two situations. Either the value is already inserted, in that case we may handle the situation depending on how we want to handle it. For instance, we may say, okay, I'm not supporting the insertion of two values having the same number, such in the case of social security number, for instance. So for each individual, we want one single social security number. So inserting two social security numbers, two equivalent social security numbers shouldn't be supported. In that case, we will return an error. Or we may say something like, okay, I'm supporting multiple insertion of the same value by doing something, for instance, as in the case of the birthday. We may have one single node representing all the possible one single node representing one possible birthday, and all the people having as birthday that day will be inserted in the same node. Okay, this depends on what you want to do, what you want to represent, of course. However, the insertion of a value in a BSD which already contain the value is almost straightforward. You simply have to search that value and then do something to insert the value you want to insert. If we have a situation in which the value is not already contained in the BST, things are a little bit tougher, but not that much, as you already saw, probably. For instance, in this case, we want to insert the number 3 in a BSD which does not contain number 3. We need to search for that value. We end up with nil, and with a nil leaf. And so what we can do is simply replace the nil leaf with a new node containing the value we want to insert. So in both the cases, the insertion is simply done by searching the value on the BST, and once we have found the node representing the value, we insert the new value, or in the case the node we end up by searching that value is the nil value, we simply insert a new node containing the value we want to store, and that's it. So what's the complexity? This is the code. I don't want to go through the code. Rather straightforward. This part is rather similar to, so the while loop is rather similar to the code for searching the value, but due to the fact that we may want to insert multiple times the same value, we need to slightly change the code here. And what's the complexity of all this stuff? Well, the complexity of all this stuff is, of course, big O of 8 of the 3, as in searching for. So once we inserted the node, well, once we are searching for the node, if we end up in a situation which x is equal to nil, we need to add a new node, and the complexity of adding a new node, of course, is theta of 1, as we saw. So the overall complexity of inserting a node is basically the complexity of searching for the correct position, the right position to insert the node, the value, and that's takes time big O of 8 of the 3, as in searching. Okay. Now we understood how to search a value inside our BST. We understood how to insert a value inside our BST. Now, how can we remove a value from our BST? That, again, this is quite easy. So we have two possible situations. Either, so let's assume we want to remove a key. And first of all, we need to search for that key. Okay. Then we have two possible situations. Either the node containing that key has at most one child, for instance, this case, so let's assume we want to remove the number 2, value 2, and in this case we are dealing with a node whose which has only one child, which is this one. So removing this node is quite easy. We simply have to delete it and replace this node by this node, so it's child. Okay. Again, how can we do it? Well, we can do it by using the procedure set child we saw at the very beginning of the discussion. By using the procedure set child on this node and on this node, we are able to set this node as left child of this node, and in doing this we are basically deleting this. Okay, this is quite easy. So once you understood the node you want to delete, which takes time big O of 8 of the 3, of course, removing the node in this case takes time, takes constant time. Straightforward. Let's assume we want to, and this is a possible scenario. What about if you want to remove instead of 2 the value 1? Well, in this case apparently we don't have any child, but again, since we are able to we are representing the leaf of DST as nil, to remove this node is quite easy. We simply have to replace this node by nil in this way, and this is again straightforward. Simply we can again apply the set child procedure on this node and this node, and we end up in a situation in which this node is removed. Straightforward. So again, also in this case, so in both the cases in which x has one child or x hasn't child, the complexity is big O of 8 of the 3. What about the case in which x has 2 child? So let's assume we want to remove the number, the value 3, and the value 3 is stored as key in the root of the 3. Well, in this case, of course, we have 2 children. So how can we remove it? Well, a possible strategy is to find the successor of this node. Well, the successor of this node, as we already understood, can be found simply searching for the minimum. Since we are in a situation in which this node has 2 children, of course it has the right children, so we can find them the minimum among all the nodes on the right subtrees, and this is it. So this is the successor of the node we want to remove from the tree, and and so we can simply assign the key value of this node to the node we want to remove in this way. Okay, now the value which we want to remove from the BST no more exists on the BST, and we are left with the two nodes having the same values, which is the root of the tree and this node. But we may remove this node, so the node which was the successor of the node we were dealing at the beginning, simply because it's easier. This node can be easily removed because for sure it has less than 2 children. Why it has less than 2 children? Because otherwise it couldn't be the minimum among all the values on the right subtree of this node. So since this is the minimum, for sure it has at most 1 children. Okay, and in particular is missing the left child, and that's why it has at most 1 children. And since it has at most 1 children, it is easy to remove, because we saw before how to remove nodes having at most 1 children. It can be done simply by taking in this specific case, taking the right children and replacing it. So this can be done this way. Okay, so we understood how to remove values, and this can be done simply by searching the node containing the keys and then considering these two cases. Either x1 has at most 1 child, and in that case we can simply remove the node itself by its child, or it has 2 children, and then we can find the successor of that node on the BST. And once we found the successor, we copy the key value of the successor on the node we want to remove, and we remove the successor of the node we were dealing at the beginning. Okay, and this is all. Now, how can we do it? Well, we can do it by using this procedure, which is the transplant procedure, which is basically meant to replace a given node by another node. It's quite easy. So if we want to replace the root of the tree, we simply have to by y, and the root of the tree is x. Well, we simply have to assign to the tree root y, and then if y is different from nil, of course, we have to assign to the parent of y the value nil. This is conventional, since we now having y as root of the tree we are dealing with. If this is not the case, so if the node we are going to replace is not the root, of course we can first of all test evaluate the childhood side. So meaning we need to know whether x is a left child or right child, and once we evaluated the childhood side of x, we may use a set child to attach to x parent the new child on the same side in which x was. Okay, so what's the complexity of this stuff? Well, once you have x, once you have y, the complexity of this stuff of course is constant, because this operation is constant, this operation is constant, this operation is constant. So this takes time theta of 1, and this is the procedure to remove a key from to remove a node, let's say, from the tree. So the total, as we saw, the transplant procedure takes time theta of 1. the minimum in tree procedure, which is used in the case in which we have exclusively one child, takes time big O of 8 of the 3. So so in the general case, removing a node, or better, removing a value from a tree takes time big O of 8 of the 3. Okay? And this is it. So right now we know how to create a BST, which is quite easy. We simply have to assign to t root value nil. We know how to insert a value. We know how to search for a value. We know how to delete a value. And these are the complexity for all this procedure in a BST. Now the point is, what's the complexity? What's the height of a BST? Well, unfortunately, the height of BST can be equal to the number of nodes stored in the BST itself. And this is quite easy to see. So let's figure out a situation in which you have a BST and you keep inserting a value which is the largest among the values stored on the... Well, you keep inserting a new value which is larger than all the values in the BST. So you first insert 0, then you insert 1, then you insert 2, then you insert 3, and so on and so forward. So what are you doing? You are keeping inserting value on the rightmost branch of the tree. And so at the end of the insertion, you end up with a chain, basically. And so the height of the tree is equivalent to the number of values stored in the tree itself. Okay, so you may think that this is a quite unlikely situation, and we are in some sense guaranteed by distribution that this does not happen in many cases. However, let's go back to our motivation. We were trying to build up a data store, a database to store personal data according to birthday, and of course each insertion occurs after the day in which a person has its birthday. So the insertion according the birthday are always performed at that day. So you are keeping inserting at each newborn, you are keeping inserting a value on the rightmost branch of the BST in that case. And so inserting and searching and deleting values from that BST end up in a complexity which is linear with respect to the number of values stored in the BST. So in the number of number of persons stored in the database, which basically means if you are dealing with the database recording all the persons in the world, you end up in performing for one single insertion a number operation which is linear with 7 billion. Okay, which is not really smart, and let me show you why it's not that smart. This takes time. This complexity is much more than what you get by using single list. Why? Well, if you use a single list to represent your database, so each element in the single list is a person Of course, searching costs at most big O of n. So at most cost the cost of performing a search in a single list is up to big O of n, because to search a specific day you need to go through all the elements on the list itself. Okay. What about the deletion? Again, to delete a value from the list, you need to go through all the list. So again, is big O of n. What about insertion? Well, if you are not really interested in getting a list sorted in any way, you simply have to attach your newborn at the beginning of the list. So the insertion takes constant time in that case. So BST basically costs more than single list lists. And so despite the promising beginning, and despite the smart idea of having a BST property for searching inside our BST, we end up with a data structure that is not really useful. And the point is that the height of the BST can be maybe up to the number of elements in the BST itself. So we need a way to, in some sense, balance the BST. So we want to bring the height of the BST to be more or less logarithmic with respect to n, which basically means that we want to have the length of each branch from the root of the same order. Okay, how can we do it? We can do it globally. So a possible way to do it is to balance the whole BSD after each insertion or deletion. Okay, so I insert a newborn, I test whether the BST is balanced, so whether the length of each branch in the BST is more or less of the same order. This is not clear what I mean, but I mean, it's not formally defined what means having two branches of the same order, but you may figure out what's going on here. And if this is not the case, I perform some kind of operation of the BST, trying to balance it. A possible strategy would be to visit the BST in order, and to visit the BST a possible strategy would be to visit the BST in order, building up an array, and use a sort of dichotomic strategy to build up the new balanced BST. So I build the array corresponding to BST, I take the median element, and that will be the root of our new BST. Then I go through the first part of the array, I take again the mean, and that will be the left child of the root, and so on and so forward. That could be a possible strategy, but of course it may cost a lot of time, because you have to rebuild the BST, you have to spend at least theta of n in building the array, performing operation this way. Okay, so it's not really a good strategy, especially because you may figure out a situation in which an insertion occurs quite often. So performing a big O of n operation each time you insert a newborn, for instance, is not ideal, let's say. Another possible strategy is to balance the tree locally, meaning that you balance only the unbalanced part of the tree. So instead of trying to rebuild the tree from the scratch and balancing it from the top down. Here we are trying to balance it locally. So once we discover that that the BST contains an unbalanced part, let's say we try to fix that unbalanced part. Okay, and this is a possible strategy, which, however, is not that easy, because how do you know if sub tree of the whole tree is unbalanced? How can we get it? Okay, and in particular, how can we handle the branches lengths? So a possible solution would be to use what is called BS3, red-black tree. So what's a red-black tree? Red-black tree is basically a BST which has some more features, some more properties, allowing us to deal with unbalanced situation. Okay, so the goal is to move from BST to a new data structure which should be able to guarantee the balance of the tree itself. And the idea is to do it locally. So instead of rebuilding the whole tree at each insertion and deletion, we want to fix the unbalanced part of the tree every time by inserting or removing a new node. We enlarge, or we stretch, or we reduce too much the length of a branch. Okay, and this can be done by red-black trees, which are, as I said, BST satisfying. Can you follow me? I miss you for a while. Are you still there? Please say something, because I lost you for a while. I don't know if you can follow me. Okay, how many on my talk have you lost? Okay, I just want to know how much of my presentation you lost. Not that much, some seconds. Okay, great. So we were saying that we want to move from BST, which is an already known data structure, because you implemented them during the first part of the course, to a new kind of data structure. We understood that basically they are useless, okay, because from the asymptotic point of view, you can do anything you do by using BSD, by using a single list, a linked list. So they seems to be totally worthless to implement. However, we are moving from BSD, which has had some nice ideas, to a new kind of data structure called red-black tree. So what's a red-black tree? A red-black tree is basically a binary search tree in which each node is either red or black. This is just a property, I mean, doesn't mean anything. And this property, so the color of the node, will be used to check whether a node, whether a branch is a subtree is balanced or not. Okay, and we will see how. So the point is that each node is either red or black. The root will be black for sure. All the leaves, which are nail nodes, should be black. Okay. All the And again, leaves are not, so the nil nodes are not really necessary, but they are useful to have a uniform handling of all the possible situations. Otherwise, we would be forced to include a sort of many cases, many special cases to dealing with situation in which the uncle of the node does not exist, and so on and so forth. So to avoid all these possible situations, we include nil nodes, and all these nil nodes will be, so the rectangle we saw before, and all these nil nodes will be black. So a quite important condition is that all the red nodes must be black, must have black children. Okay, so if a node is red, all both its children should be black. And another important condition, which is a condition on the tree that would be easily maintained, let's say, is that for each node in the tree, in the red-black tree, all the branching moving from that node will contain exactly the same number of black nodes. Okay? And this is a way to say that all the subtrees of the red-black tree should be balanced, but not balanced with respect to the whole nodes, but balanced with respect to the black nodes. Okay. Okay, let me define then what is the black height of a node X, and the black height of a node X will be the number of black nodes below X in any branch. Since all the branches moving from X has exactly the same number of black nodes, we can define this notation, this notion, and saying that for all the branches moving from X, we will have exactly this number of black nodes. Okay. Now, just to have an example, this is a red-black tree. As you see here, we are having red and black nodes. This is quite likely a BST, as you can see. Simply we colored the nodes, and moreover we have the property that from each node the number of black nodes from that node down to the leaves are the same for each branch. So let's move on this branch. For instance, we have 1, 2, and if you want 3 nodes. Let's try 2 black nodes, of course. Let's move on this branch, which is shorter because of course here we have 4 nodes. This branch we have 3 nodes, and this is 1, 2, and 3. All of them are black. What about this branch, for instance, which is by far larger than this branch? So in this branch we have 3 nodes, in this branch we have 1, 2, 3, 4, 5 nodes. But again, the number of black nodes are the same. So here we are having 3 nodes, and here we are having 1, 2, and 3 nodes. Okay, so this is a red-black tree which respects the definition. Okay. Now, of course, again, as we did for BST, in dealing with in trying to represent a red-black tree, I from time to time I will remove the leaves. So it could be the case that you can see a red-black tree without the nil leaves, and this is due to the fact that I don't want to waste space in the slides, okay? But of course they are still there. Now, seeing this definition, this example, we may want to define another useful function, which is the color of a node. Oh, by the way, we need, of course, to enlarge our data structure to store the new property, and this is done by using this notation. This notation basically return the color, contains the color of a node which is different from nil. This procedure is simply done for uniform dealing with standard nodes and nil nodes, as you can see here. So by calling color on any possible node, being either a standard node or a nil node, I get the correct color. So the color of the nil node will be black, as you can see, and the color of any node will be the value stored in this member of the data structure. The cost of this function, of course, in execution time is constant, for sure, because it's just a conditional statement plus 2 returns, so it doesn't cost any more. And this is useful, and we will see why it's so important to have this function, which is, I mean, straightforward. Now, we saw that BST may have as length a number of values stored in the BST itself. So a good question would be, what about regular trees? So what's the maximum height of a regular tree? And it's easy to prove that a regular tree within any internal node has at most 8 2 multiplied by logarithm base 2 of n plus 1. And this is quite easy to prove, because we can prove by induction that the subtree rooted in each node in the regular tree has at least this number of internal nodes. So if I'm dealing with a leaf, I'm dealing with 2 at the power of 1 minus 1, which is 1, and so the subtree rooted in a leaf end up having at least one node. If I'm dealing with something which is not a leaf, well, of course it's right subtree, and its left subtree has height 8 equal to the 8 of x minus 1, so I can apply by induction the property, and I end up in dealing with I end up improving this property, basically. So once I prove this property, to get the theorem, I need simply to observe that the Blake height of any node is at least half of the height of the node itself, and this is because for sure we know that any red node must have as children black nodes. Okay, so this value is at least half of the height of x, and so it turns out that we have this equation, and this is due to this property. So by applying some algebraic stuff, we end up with this value. So this means that the height of a regular tree has 8 and most logarithmic with respect to the number of values stored in the tree itself. Okay, which is nice, because if you remember, talking about the insertion, deletion, and removal of values from the regular trees, the complexity depends on the height of the tree itself. So if we use regular tree and we are able to update the insertion, the deletion, the insertion and deletion procedure in a way in which from a regular tree we are able to end up with a regular tree, we are guaranteed that the insertion, the deletion, and the search in the regular tree takes time logarithmic with respect to the number of values stored in the array tree itself. Okay, so tomorrow we will see how to do it. So the goal of the lesson of tomorrow would be to try to find a way to insert value inside a regular tree, preserving the regular tree itself. So we will start from the regular tree, we will try to insert values inside the regular tree, and we want to end up with binary search tree which respect all the property of the regular tree. So we want to end up with another regular tree. Okay, and that's all for today. So I hope you enjoyed the lesson. I hope that I know we repeated a lot of stuff you already saw during the first part of this course. However, I thought that it is important to go through all the stuff again from the scratch, especially because since we are going to talk about regular trees, and regular trees are basically binary search trees, many procedures with that we are going to use in dealing with regular trees are basically coming from binary search tree, and that's why I decided to repeat basically what you already saw. So let me know what's going on with you, if you can follow me, if everything is clear, if you need some more explanation of some part of what we saw today. And moreover, I really would like to stress that it's important for me to know what's going on with the homework. We may find a way to solve the problem of the load of the work homework exclusively if I can understand where is the problem. Okay, so if the problem is the load, I mean they are too much, we can decrease them. If the problem is that they are too hard, we can find a way to try to solve some of them all together. Okay, it's just up to you. Let me know what's going on, and we will try to fix them. And that's it. So see you tomorrow. Thank you for the attention, and that's it. Okay, thank you.